Now, all right, this should be recording. I think, yeah. Alrighty, move this over. All right, so let's go ahead and move on to the review session packet. The first thing we are going to be covering are shapes, bond angles, and hybridization. Oh, I forgot. I need this one file open. There we go. Okay. Now, the magic hybridization and bond angles you're going to be looking at are these ones right here. SP as 180 degrees, SP2 120, and SP3 109.5. Those are the ones you're just going to be mainly looking at because they're very correlated. And even though there's a bunch of mumbo jumbo here, like, you know, kind of close enough to 109 or a little less than 109.5, that doesn't really matter because we'll accept both because we mainly just want that number and that concept that you know what that angle is. All right. And the thing for distinguishing shape and like bond angle, because as you saw in the problem set, you can have a trigonal planar bent atom be 120 degrees, but the bent molecule of water is 109.5. That's a little difficult, but the distinction we want to make is that the bond angle is just mainly correlated with hybridization. Bond angle, hybridization. So that's all you have to worry about. So bond angle, even though it sounds kind of weird, don't take it from the shape. Take it from the hybridization. Because you know, let's go and do this first one. Maybe you guys can have a better idea if you see it. So for sulfur dioxide, let's go ahead and just work through it as if we're going through it on a normal problem set. So we have sulfur, which is 6 electrons, oxygen, and we have 2 of those, and you each have 6 electrons. And total, that's 6, 12, 18 valence electrons. And our central atom is sulfur. And it's usually going to be a heteroatom like sulfur, phosphorus, anything that can obviously hold more than, or that can exceed the octet. So group 3 and above are pretty good.
Do your hair.
Oh. Hold on. That can exceed that octet, or stuff that's not really halogens, hydrogens, or oxygen. Because even though oxygen can be a central atom, like in ozone, as you noticed, halogens and hydrogens are kind of like blunt ends or dead ends to like a compound. So if you have like an entire carbon chain, right? Well, H's and halogens, that's supposed to be an H, can plug up those loose bonds because just they only form one bond. And they're more seen on the outer portions of the compound. Same thing with oxygen. So we have sulfur and oxygen. There has to be at least one sigma bond between them, or else it's not part of the, or else it's not part of the compound. So that's already 1, 2, 3, 4 electrons. That's 14 electrons left. If we were to make them double bonds, that would be another 4 U's. That would be 10 electrons left. So if we were to just apply them to the outer atoms first, 1, 2, 3, 4, 5, 6, 7, 8.
Right.
The oxygens have full octets, and we just put them, the last 2, on sulfur. Now, if we look at sulfur, all right, what is the hybridization of sulfur? Someone just blurt it out or type it in the chat. Hold on, let me see if I can pull chat up.
I think it's SP2.
Right, it is SP2. Because hybridization comes from the electron groups. So electron groups being lone pairs, single bonds, double bonds, or triple bonds. So even though a triple bond has 2 more pi bonds than a sigma bond, they're each both of them are in it themselves an electron group. Excuse me. So 3 electron groups, and that gives us our hybridization. And from hybridization, we get bond angle. So the hybridization of sulfur is sp2. All right. Now let's draw the shape. If we have sulfur, let's see, sulfur, oxygen, oxygen, lone pair, 3 electron groups, that's sp2 trigonal planar. If it's trigonal planar, then it's really flat. However, one of those branches is an electron pair or a lone pair of electrons, and that's invisible to us in the naked eye. Not, well, all of this is invisible to us, but experimentally, we don't really observe it interacting with a bunch of other stuff related to that. But 3 electron groups, this one's basically invisible, so it's going to be a bent shape. You guys did the problem set. You guys know this. And the bond angle, sp2, what is the bond angle of an sp2 hybridized atom? Yeah, 120. All right, that's it. Now let's move on to the next one. NO2. So nitrogen has 5 electrons. Oxygen, again, we have 2 of these and 6 electrons total. So we have 5 plus 12. It's going to be 17 electrons. However, the thing to notice is that there's a charge. There's a +1 charge there. So it's missing an electron that it normally has. So it was oxidized. So we have actually 16 valence electrons. All right. So central atom, nitrogen, and it needs at least 1 sigma bond with all the other atoms. That's already 1, 2, 3, 4. We have 12 left. We make these double bonds. Another 4, 8 electrons left. 1, 2, 3, 4, 5, 6, 7, 8. That uses up all of our atoms. However, the thing to note for all of these is formal charge. Nitrogen likes to have 1 lone pair and 3 bonds just in general. But this nitrogen does not have any lone pairs at all. It has an extra bond than it normally wants. So there is a positive formal charge. There's a positive formal charge on here, then there's only the 2 electron groups left, these double bonded oxygens. So what hybridization is it?
SP.
Yeah, it's SP. And it's just SP. That's just 2 bonds. There's 2 bonds. It's really easy. I'm not going to quiz you guys on this. You guys know this. It's just going to be bent. Not bent, linear. And the bond angle would be?
180.
Yeah, 180. All right, let's go on to these. Now, I don't mean to get your hopes up if you're good at this, but I'm pretty sure it's safe to say you will see this on the test. This is a very popular type of question that he loves throwing at us. So let's just go ahead and get into it. The hybridization of C7. Before I get into that, I really always just draw the lone pairs. It's either going to be on oxygen or nitrogen, and sometimes your compounds will have both. So for this one, I identified all the oxygens. I drew the lone pairs. So I'm aware that they exist and that I know their hybridization. Oxygen 1, for example, this question right here, what's the hybridization? That's sp3. So that is a tetrahedral shape, but because the lone pairs are, well, electrons, it's invisible to us and it looks bent to us. So we know that even though this is written out in a linear path, it's actually bent. And this one is sp2. But it doesn't ask us about that. It's asking us about C7. C7 has 3 electron groups, 2 sigma bonds, and then 1 sigma bond with a pi bond around it. What hybridization is that?
sp2.
Yeah, sp2. Good. And then this one, what is the bond angle between C6, O2, and O1? What is that bond angle? Here, let's identify this real quick. That's an sp2. And remember, bond angle is always derived from its hybridization. If the hybridization is sp2, bond angle is 120. And for C4, C5, C6, right here, let me erase this. There we go. Well, the central atom C5, that's sp3. And remember, again, its bond angle is correlated with that hybridization. If it's sp3, it has to be 109.5.
So,
All right.
so In order to like identify like the bond angles, then all you have to really do is identify the hybridization of the central atom.
Yep.
And that'll just, if you're like familiar with the hybridizations and the.
Yeah, that's basically what you just get the hybridization and you get that angle from that.
Thank you.
Yeah. And then C7 right here, we did identify that as SP2. SP2 always correlated with 120 degrees. Here we go. All right. Which carbon is primary? Ooh, this brings back our primary, secondary, tertiary. And even though he kind of glossed over that, I will say, literally, this is probably one of your biggest concepts in OChem, especially when you get into reactions and reaction rates. There are preferences. We want a primary carbon, a secondary carbon, or a tertiary something, because that deals with the chemistry and its reactivity. So this is really good practice and something that you should really get the hang of. So primary is if it's connected to one carbon. So by looking at this, which one is primary? Don't count the alkene, because we're going to get to that.
Is it C1?
C1.
Yeah, C1. Good. All right. Now let's move on. Now, I hope you guys are big fans of acids and bases, because that's also a really big concept that OChem is pretty big on. If you're good at Gen Chem acids and bases, you'll kind of get the hang of this one. It's pretty nice. If you kind of sucked at acid and bases, especially titrations and stuff, it might take a little work. It might take a little work, but we'll get there. But thankfully for OChem, there's kind of an easy pattern we can look at, mainly for the Lewis acids and bases. But for the first definitions, Bronsted-Lowry acids and bases are the ones that you guys have always been dealing with in Gen Chem. Proton donators, proton acceptors. So just releasing or taking a hydrogen. That's really easy. Excuse me. Do you guys have any other examples of proton donors and acceptors? Not that. Strong acids, strong bases. I'm tripping. Someone want to, yeah, you guys just blurt out the strong acids and bases in chat. I want to see what you guys know, because I TA for Gen Chem as well, and I want to make sure people are on top of that. Yeah, HBr, HF, not HF, HCl, great. HBr. So all of the halogen acids are strong acids except HF. HF is the one, yeah, that's a weak one. Sulfuric acid. We also have nitric acid, HNO3. Don't worry, Jim. HNO3 and perchloric acid, which is HClO4. Perchloric acid we don't really see. And the strong bases is pretty much OH with any of the group 1 and cations, but mainly you'll just use NaOH. KOH and NaOH are the ones you're going to see. Strong bases are not that big of a deal, because you can honestly just write OH and we'll know what you're talking about. But this is the kicker. Have you guys done any practice tests where it's asking you identify the Lewis acid? And it gives you like an entire list of stuff. Yeah.
I was listening to one of them, and then he gave us like a really weird specific list in the notes one time.
Yeah.
And I forgot about it.
Don't worry. I'll tell you like a cool little pattern. But off the record, if any future TAs or Dr. Berg sees this, I'm sorry about my language, but fuck those questions. I hated that. The pattern for knowing a Lewis acid and Lewis base, well, for Lewis acid, lone pair acceptor, is you have a central atom and it's connected to 3 things, usually halogens. This is the pattern, because the main thing for this is that the central atom, incomplete octet. That's the biggest giveaway. And these X's are going to be, again, halogens. Rarely you'll see hydrogens. You'll see BH3. That's an example of this hydrogen, but it's usually going to be, or hydrogen, it's usually going to be a halogen here, like FCl, Br. because they just plug up the ends of bonds. And you just have 3 of them. Well, that central atom has an incomplete octet. So for the central atoms, the really common ones you will see: boron, aluminum, iron. Yeah, those are the main big ones. Maybe some silicon. So some examples would be, let's do silicon. Use black. Silicon. Try. There we go. Right here. So silicon, well, that would actually have a formal charge of +1. So cations are also pretty good Lewis acids because if you remember Gen Chem, cations are usually acidic. Mainly for this point, they are electron pair acceptors. So if we had, let's say, a lone pair on ammonia right here, ammonia is a perfect example of a Lewis pair donor because the converse of our definition for the Lewis acid, the central atom will have a lone pair that can make a bond with. So that will form a bond with that. We'll get silicon, H, 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 N, H. Now, this is a hypothetical reaction, but this one would have a formal charge. Do you guys know where the formal charge would be? What atom? Could be nitrogen. Because nitrogen has 4 bonds there. Doesn't really want that. So it has a positive formal charge. But do you guys want to throw up here? Let me give you some examples and maybe I'll have you guys throw some out. So AlCl3 or BF3. Again, central atom, 3 halogens, or let's do FeBr3. Semester 2, these are all solvents and acid catalysts that you will use, so you'll see them again. But do you guys want to throw out any examples in the chat? Just like pick any central atom that's not group 2 or below and just slap 3 halogens on it. Like PCl3. PCl3 you'll see this semester. Or, ooh, let me think. FeCl3 works. No one's throwing anything in chat. That's okay. If you rewash this, just write down this pattern. You should be able to figure it out. All right, let's move on now. Okay, so for labeling acids and bases and knowing the direction, my biggest hint or tip is just basically identify the acids. Because when you were doing problem set 2 and you had to write the pKa's and you had to pick, all right, does it go left or does it go right? You just look at the acids because acids are the ones that dissociate. And for these reactions, you'll pretty much always see a Bronsted-Lowry acid-base reaction. You don't have to deal with the electrons, at least not yet. So honestly, for just looking at pKa, just look at the acids because for the conjugate bases, looking at the pKb and then converting it to take the inverse of the pKb is too much work. And just look at the pKa's, it makes things a lot easier. Yeah. The acids and bases. Yeah.
So are you saying like whichever side the strong acid is on, it'll just go in the
Push.
it'll go in the direction of the other side?
Yeah, it'll go away from it.
Okay.
So for example, HNO3 plus F minus HF plus NO3 minus. Identify your acids: nitric acid, hydrofluoric acid. This pK is a lot smaller. Let's say it was like negative, what, 1.6? Right? And if this was not, let's just say the pKa was 2. I don't know the actual value, I'm sorry, but let's just say it was 2. This pK is a lot smaller, so it's a lot more acidic. So the entire reaction, I don't know why I drew that plus, but the entire reaction would go away from it because it dissociates the most. It'll decompose the most and it'll push everything away because it likes being in its stable conjugate base form in a solution. So just identify your acids and pick the lowest one, or in terms of pKa, and choose the arrow away from it. And using our knowledge of what we just talked about for a Lewis acid, which of these is a Lewis acid? It might help if we drew them out. Okay, so let's draw these out. And H C CH3 and CH3OH. All right. So out of these three, not three, out of these four options, which one is a Lewis acid?
Third one.
That's correct. And that is a carbocation. And as you can see, the central atom has 3 bonds and it has an incomplete octet. So it's more readily available to accept an electron because it's deficient in it. And any floating electrons on some kind of molecule will be more attracted to that positive end. Is that making sense for everyone? Hopefully you guys are nodding. You guys are on Zoom, not in person. I had someone ask me to go back. Can you explain the acid-base reaction? Can you go back and answer the question on carbon chain in the second question? Caitlin, are you talking about the Bronsted-Lowry acids and bases?
It was the question underneath that long carbon chain, and it asked to circle like all the atoms that are in the
shit.
same plane.
I just glossed over that. I'm so sorry, guys.
No, you're good.
I'm looking at my notes at it right now, and my chat box was covering it. My bad. Well, it's really easy. If you guys watch the video, hopefully you guys can watch it after this. But the magic numbers you're looking for the same plane are SP and SP2. Because SP and SP2 are all planar. SP is obviously linear, so it is planar. And SP2 is trigonal planar, so it's all in the same plane. And the plane breaker is SP3, because SP3 is tetrahedral and it'll bend shit. All right. So if our reference carbon was carbon 6, that is an SP2. And if carbon 6 is an SP2, every atom around it must be within the same plane. So all these bonds are in the same plane. So C5, O2, and O1. All right. Now let's analyze the hybridization of the surrounding ones. So O2, that is an sp2 hybridized oxygen, but it's not connected to anything. So we can just stop it right there and just keep that circle. C5, that's an sp3 carbon. So even though C5 is in the same plane as C6, every atom it's bonded to is in a different plane. So this is bent, and this is bent. So it just ends there. Same thing with oxygen number 1. There's a lone pair, 2 lone pairs here. It's sp3 hybridized, is bent like it is in water. So every bond it has with every other atom is bent, except the one with C6 because it's on the same plane. An example I went through in the video is if we hypothetically just imagined O1 as sp2, so we can continue the chain. All right. So magically, let's just pretend O1 is sp2 and we just kept it going. All right. Let's just say it's linear. Then that means if O1 was linear, then every bond around it is in the same plane. So this bond, and we identified that bond. So C7 must be within that same plane as O1. And by the transitive property, C7 must be in the same plane as C6 as well. Now let's analyze C7. C7 is sp2. That's in the same plane. This is one of the magic hybridizations we're looking for. So every single bond that C7 is attached to is in the same plane. So this hydrogen and that carbon is the same plane as C7, and thus by transitive property, same plane as C6. And we do the same thing again. C8, that's sp2. And that means this bond, this bond, this bond, all in the same plane. So these hydrogens must also be in the same plane as C6 by transitive property. However, this is not how the question was designed. O1 is an sp3 hybridized oxygen. So everything that's connected to the oxygen is not in the same plane, just that one oxygen. Does that cover everything? Or any questions regarding this?
I know you said it wasn't important, but earlier when we answered that bottom question on the left that says C1 on that same question, what is the 1' carbon?
Mhm.
You said we didn't have to worry about C8, and why was that?
Um,
Or is that like not?
I think they are primary, but analytically the alkene messes with some rules. But the main thing, I don't want you guys to worry about that just yet because I don't want to overload you guys.
Yeah,
with
if it's not important, like screw it. But
What's up?
just- I said if it's not like if we don't have to know it, then like it's whatever. But I was just
Yeah.
kind of.
I want Dr. Berg to explain it because if I say something wrong, then it's gonna mess up your understanding from what Dr. Berg says. So we'll get to that later.
Well, that's all right. Thank you.
All right. Now, acid strength, this is a little bit of a toughie. All right. So when we are comparing acids that are in the same group, so if you guys have your periodic table right now, let me pull this one up. If you're comparing acids within the same group right here, size only matters when you're going down. Right. So let's take nitrogen and phosphorus. Let's just say we have these atoms, nitrogen. I don't know why I did that. There we go. And phosphorus. Let's just say these are, I don't have a lot of room here. Let's just pretend that those are bonded and they're neat. All right. So if they're in the same group and it's asking which one is the most acidic, well, if they're in the same group, the one that's lower is the most acidic. So phosphorus is the most acidic. And that's the only way size matters. Okay, that just came out wrong. That is one of the situations where size matters. Okay, when you are comparing down the periodic table. So if you have like H2O versus, thank you, Gavin, H2S. You'll see later, he will say it. Size matters. You'll get into it test too, don't worry. But anyway, if you have something like this, H2O versus H2S, which one's more acidic? It's going to be H2S. Electronegativity is comparing acids across the periodic table. All right. So those are going to be like NH bonds versus OH bonds. All right. So an example of that would be, let's say you have an alkane, and let's connect it to a amine group. All right, and then you have an oxygen. All right, these are in the same period. However, for this case, which one's more electronegative? It's going to be oxygen. So this is the most acidic species because they're in the same period, but they're in different groups. So the more electronegative one is the most acidic one. All right. Does anyone have any questions regarding that? I know I just erased it, but I can go back. Okay. Let's move on to hybridization. Hybridization just talks about P character. And this is really easy. SP is more acidic than SP2. And SP2 is more acidic than SP3. That's it. So like an alkyne, CCH, is more acidic than methane. You'll deal with that a lot more later on, but just know that this hierarchy, SP, SP2, SP3, that's all you have to know regards to which is more acidic for hybridization wise. I'm just making myself more room, by the way. Now, these two big ones are going to be the inductive effect. Now, this is present when you slap an electronegative atom on a species of a compound, that is. So if you have, work with me, OH, for example, let's do carbonyl here, and let's do BR. All right. Same deal. Let's do fluorine. It just basically says the most acidic one has the most electronegativity being pulled away, and the most the electron cloud being pulled away correlates with the more electronegative species being slapped on. So the difference between these are obviously the halogens. fluorine is a lot more electronegative than bromine. So that pull is going to be a lot greater than bromine. So if that pull is going to be greater, the electron density is going to go farther away from the hydrogen, and this hydrogen is going to pop off a lot easier. We can do another example. Remember, the inductive effect correlates with acidity. So let's, I'm just a big fan of pentanes, aren't I? Let me think of a interesting one. Okay, I got one. Let's do Cl. Oh. Let's make that an ether. All right. Which one is more acidic? Oh, that's a bad question. Hold up. Let me do fluorine. It should be fluorine. My bad. Okay. Now that makes a lot more sense. Fluorine. Which one is more acidic?
The one on the left.
Yeah, the one on the left. Fluorine is a lot more electronegative than oxygen. Resonance structure. So the more resonance structures the conjugate base has, the more stable the base is. And the more stable the base is, the more the compound wants to be that stable base, and the weaker the base. So basically, going through like a big chain of logic, conjugate base, stable base, weaker base, stronger acid, the more resonance structures it has, the stronger the acid. That's the only fact you have to like whittle down. For example, let's do, no, that's not a good resonance structure example. I can't think of good ones. I'm not good at making resonance structures out of the blue. Do you guys have any questions regarding this? I'm going to try to think of one. Oh, I just thought of one. An alcohol versus a carboxylic acid. All right. So on top of the electronegativity being pulled away from that hydrogen by that carbonyl oxygen, it also has resonance. So when these protons are eventually popped off, right? So let's just say we pop them off and we have a residual negative charge on them. Which one is the weaker base? This one is the weaker base because that resonance flip-flops between the two oxygens. So the more resonance it has, the more stable it is. And the more stable it is, the more stable or weaker that conjugate base is, the stronger the acid. So the original acid is much stronger. Anyone have any questions on that?
Well, yeah, I'm sorry. So you said that the original acid is stronger because it has resonance, correct?
The conjugate base has resonance.
Okay.
Yeah.
So if the conjugate base has resonance, that means
The original
it's
acid.
because it's a weaker base then?
Yeah, because it's
Okay.
weaker. I think the key should also be posted. The key just like basically draws that line of logic for you if you want to go down that. But I think you should know that for the test, but I would focus more on the inductive effect. That's a bit of a more important concept. But let's just move on to which is the strongest acid. All right, so oxygen, sulfur, and I think is that selenium. Let's go down. Yeah, selenium right here, these three right here. So they are all in the same group. Thus, we need size. Size matters. We need size to determine which is more acidic. So the lower one is the most acidic one because they're all in the same group. And that would be H2.
SE.
Chat. SE, yeah. Which of the following is the stronger base?
Chlorine.
What's up?
Chlorine.
Yeah, chlorine is a stronger base. It's more unstable in a solution than bromine because bromine has a lot more size to it, has a lot more electrons, so it's stabilized by more hydration shells. That's in a solution. Now, it gives us this equilibrium table right here. Now, we're looking at where it shifts. Again, the first step is identifying your acids. What are our acids here? NH3 and H2O. We identify the acids. We don't care about everything else because these two are what the pKa's are correlated with. The pKa of NH3 is 38. So it's really, really high and not very acidic. The pKa of H2O is 15.74. Relatively low. So, excuse me, NH3, H2O. Which one is the stronger acid?
NH3.
Oh, sorry.
It's water. Water is the strongest acid. The smaller the pKa, the smaller the pH. And small pHs is more acidic. You're looking for really low pHs. So you know how like all the strong acids have negative pKa's? That should give you a hint on which direction you're kind of looking for strong acids. Then a lot of like alkanes, alkenes, carbon-based compounds have pKa's like 30 and above. Those are pretty weak acids. Did I say bases before? I feel like I accidentally slipped in a base. I meant all this, I'm just talking about acids. Weaker acid, just NH3. And if H2O is the strongest acid in this solution, which way will it shift?
Left.
Left, away from the strong acid. Correct. Newman projections. These are hella a lot of fun. Yay. All right. So for this compound specifically, we're looking down the C3 through C4 bond. The front carbon is C3. Well, thankfully, this is symmetrical. So either way you go, 1, 2, 3, 4, 5. That's the same this way. There's 1, 2, 3, 4, 5. It's symmetrical. So for simplicity's sake, we just have it as it is. So the highest energy conformation is given as this. Now, we have to just draw staggered, staggered Newman projections. I couldn't find the word. And for me, I just take a look at this. I basically just copy it down. So like for this front ring, let's just keep the front ring as it is. CH2, CH3, CH3, CH3. And then this back ring, let's just keep it as it is. CH3, HH. All right, so hopefully you guys saw, I just rotated that just a little bit, just scooted it out of the way. And if this is our stationary just line of sight, if we're looking, let's just say looking this way, right, down here, we're just keeping that back part the same, and we're just rotating that front ring. So I would go ahead and just fill this in right here. You guys following? Hopefully you guys are. So we're just rotating that front one. And if we are rotating it, well, this ethyl group goes down here and so on. So CH2, CH3, CH3, CH3. And then again, CH2, CH3, CH3, CH3. And the big thing I would suggest is reading, because you have to make sure you have to circle the lowest energy conformation. Out of these three, which one has the lowest energy?
The middle.
The middle one, because it has the least amount of steric strain. So because these are in staggered formations, torsional strain is out of the picture. Now there's no bond angle strain because it's not cyclic, so you only have steric strain. And we want the biggest group the farthest away from the steric groups or the other steric groups to minimize that steric strain. So even though this is not ideal because we have methyl groups like kind of around each other, the biggest one is the farthest away, and we just keep that shit away. So it is the most stable, the least amount of steric strain. And now we get into the oh so lovable cyclohexane chair conformations. These are a lot of fun. Do you guys like these? I hope you guys do. Yeah. So hopefully you guys kind of see a little pattern going on. If you have a model set, you guys can see the pattern too, but I'm just going to draw this out. All right. Let's just say you're looking at a cyclohexane you make with your model set, just you're just fucking around with it. All right. And let's just say we have, you know, our normal sp3 hybridized projections that are just sticking out right here. Well, for everything on this top layer, they're all within the same plane, right? That's what it means by, well, same plane, they're all on the same side. So all these pink dots, if they were hydrogens, they would all be cis to each other. And the pattern goes, they alternate. So this is axial. In a chair conformation, everything next to the axial ones are equatorial. And then vice versa. For every same side pink dot that's next to an equatorial, it's axial. And then this, you just fill out, they alternate. So if I were to write the pinks here in this chair conformation, let's just do pink dot, pink dot, pink dot, pink dot, pink dot, pink dot. All right. You see how in each of the pairs, the pink dots are the ones that are facing upmost in whatever pairing they're in. They alternate. You see this axial, this is equatorial. Axial, equatorial, axial, equatorial. You guys see that pattern? That's a really helpful pattern to get the hang of, especially when you deal with a lot more complex configurations. And the opposite goes for the other conformations or the other side. These blue dots are all on the same side, but on the opposite side, the pinks. And in real life, they would be equatorial, axial, equatorial, axial. Maybe if we have time at the end, we can play around with the problem sets, but I really suggest that you play around with it watching Dr. Berg's videos that he posted.
So I have a question about those two.
Yeah.
On a couple of the practice exams, they asked which chair structure was more stable. So comparing
Ooh.
those two at the top, how would you tell which one is more stable?
The more stable one, so the stable ones, you consider methyl groups and ethyl groups. That's what they usually have. And that's when they're in the equatorial position. He might have glossed over this, but if you have like a methyl group on this carbon and an ethyl group on this carbon, the most stable conformation is when they're in the equatorial position. Because let's just say that ethyl group's right here and that methyl group's right here. They're facing away from each other. So they're not very sterically hindered. All right. And let's say this methyl group was axial, right? What if it was axial? This conformation is still the most stable because whichever one is largest, you want that in the equatorial position. You just want it to face away because axial, if you remember for steric strain, there's the 1,3 diaxial strain when they fuck up with each other. That won't happen if it's in the equatorial position. Just say it was an ethyl group. If it's in the equatorial, facing away does not deal with the ring structure at all, so it's the most stable. Does that answer your question?
Yeah, thank you.
Yeah. All right. So,
I had a question. Can you explain what exactly the ring flip is?
the ring flip basically reverses all of it. So the ring flip changes every axial position you have. Every axial atom now becomes equatorial. And every equatorial atom you have on that carbon ring becomes axial. Do you guys want to save this for the end so that I can make a ring structure and we can work on that at the end? Or do you guys just want to make it now? Probably save it for the end because this is a pretty big concept. Because the last parts is just nomenclature. And then isomerism. We're only 47 minutes and we still have an hour and 13 minutes.
Either way is fine. You can just wait till the end.
Yeah. All right. I'll wait till the end. Yeah, I'll wait till the end. Let's save this for later. Let's go ahead and get nomenclature out of the way. So for nomenclature, the first step is identifying your parent chain. In your parent chain, you have to look at the corners. Like if they're in a cuculate structure, it's pretty easy. You can kind of look at it. But when they're written out like this, it's kind of hard. Yet you just have to find the longest chain. For this one is a pentane. That's kind of a bad example, but for this one on the right, let's just say you want to go across. That's something that he will throw at you. He'll lay it out where it looks like the chain across the paper looks like the longest chain, but just look at the ends and see if you can extend that chain a little bit. You can, so you just extend your parent chain. Again, longest chain, but we can, for these ends, we can extend them even more. This one is a little bit of bad example. It's just simple alkane. You want to go there just across, but if you want this ethyl group, with this ethyl group, you can expand it into a pentane. If we were to name it, if this is a pentane with 5 carbons, we have 1, 2, 3, 4, 5. And then we have 1, 2, 3, 4, 5. 2, 3 versus 3, 4. The 2, 3 would win. So we have 2, 3 dimethyl pentane. And then for this one, again, our parent chain can cross those corners. So you have to consider them. That's 1, 2, 3, 4, 5, 6, 7, 8. That's an octane. We have an ethyl group and then a methyl group. 1, 2, 3, 4, 5, 6, 7, 8. We have a 4 ethyl, 3 methyl octane. Does anyone have any questions regarding that?
I have a quick question on the practice test.
Practice test?
For like another year. It was like a 6 carbon chain, and then there was a branch of NH, but branching off of that was methane.
Oh, a methane group. We'll get to that. I think that comes up here. Yeah, right here.
Yeah. Okay, cool. Thank you.
Yeah, we'll get to that.
Okay.
Good news, it's really easy. For halogen related chains, well, you guys know that's just the normal thing to do. We have a 4 carbon chain, butane, chlorine, and fluorine. Well, they're tied. They're both in the 2, 3 positions going back and forth. How do we break that tie? The alphabet breaks that tie. So we denote chlorine as the number 2 carbon. Butane, right? All right. For this one, we have a heptane. It's 7. We have 1, 2, 3, 4, 5, 6, 7. And then the other way around, 1, 2, 3, 4, 5, 6, 7. We have 3, 4, 5 both ways again. However, like we did before, the tiebreaker is the alphabet. What comes first in the alphabet? The M in methyl or the B in bromine? It's going to be bromine. So it's going to be 3, 4. Don't forget your prefix, dibromo. 5 methyl heptane. And don't forget the di in the bromo. Even though it doesn't play a role in alphabetical ordering, that prefix is still important and still, required to be there. If you're writing it on paper, they would take off points if you did not do the di or the tri or any kind of the prefixes. Hopefully you guys also saw my video on naming cyclic compounds. These are a little bit tough. For this first ring, it's really easy because you just start at one of the branches, obviously, and go the other way around. 1, 2, 3, 4, 5. Or if you went the other way, 1, 2, 3, 4, 5. The numbering is 1, 3 either direction. So what's the tiebreaker? It's going to be the alphabet. B in bromine comes before P in propyl. So it's going to be 1. Oh, oops. 1 bromo. 3 propyl. Whoops. I'm sorry. Propyl pentane. Cyclopentane. Now, when it comes to cyclohexanes, this one's a little tough because you have branches next to each other. And in the video, I go pretty in depth on the first point of difference because that's what you're kind of looking for. So when two branches are next to each other, one of those branches is where you're going to start. Because if you start on this ethyl branch right here, there's only two directions you can go. You can count this way or you can count this way. But the important concept of the first point of difference is that you want to go in the direction where there are branches until there's no branches. So what I'm trying to say is, let's say you have a cyclohexane. I know it's a really bad ring, but just bear with me. ClBr. Let's do CH3. Cl. If you were to start here, you wouldn't, but just hypothetically, you were. There's two directions you can go, this way or that way. If you went here, you would have another branch. If you went here, you would not have another branch. So you want to connect the dots where you basically hit the most amount of branches in the shortest distance. Hopefully that's kind of the concept you'll latch onto, because it'll come up again. You will have to name cyclic compounds again in test 2, but with alkenes. So if we were to start on this carbon right here, 1, 2, 3, 4. If you were to start at this carbon, 1, 2, 3, 4, 5. 1, 2, 4 is a lot better than 1, 2, 5. So we're going to go with 1, 2, 4. So it's going to be 4 chloro, 2 ethyl, 1 methyl, cyclohexane. Does anyone have any questions?
You put ethyl before methyl just because like alphabetical order, right?
Yeah. Yeah.
And Patrick, also in this case, if we could go around the cyclohexane either way and get the same combination of numbers, we would then prioritize naming the number 1 carbon as the one with the chlorine atom attached to it, right?
Yeah. Yeah. If it's a tiebreaker, you choose or as long as there's no alcohol or amine group attached to it, the tiebreaker is the alphabet. Yeah.
Thanks.
Yeah, the biggest tiebreaker is just alphabet.
Do you think on the test he'll like allow us to use a highlighter to
Oh, 100. You
follow the links? Yeah.
Yeah.
Okay.
He actually encourages it. In person, he said he likes seeing people bring like colored pencils or markers, because you're welcome to draw, annotate whatever the fuck you want. If it'll help. I mean, he does it, so he wants to encourage you guys to do it. So if you guys ever take it in person, good have it. All right, so let's move on to our ethers. All right, so longest carbon chain just straight across. We're looking at these carbons. There's no way we can extend it. So this is our carbon chain. It's a 4 carbon chain. It's a butane. Excuse me. 1, 2, 3, 4. 1, 2, 3, 4. All right. It's a 2-3 numbering system, both forward and front. However, we have ethoxy versus methyl. What comes first in the alphabet? The E in ethoxy or M in methyl? It's going to be the E. So it's going to be 2 ethoxy, 3 methyl, butane. All right. If we go over to this end, carbon chain just straight across, we have 9 carbons. It's a nonane. right? Number 1, 2, 3, 4, 5, 6, 7, 8, 9. Blue 1, 2, 3, 4, 5, 6, 7, 8, 9. Which way would we go? Black or blue?
Black.
Black. Because it gives us the lowest numbers. It's a 3, 6 versus a 4, 7. 3 methoxy. 6 methyl nonane. Now we get into the interesting stuff. Functional groups. The two functional groups you have to know is alcohols and amines. If an alcohol is on a chain, that has to get the lowest number possible. Same thing with amine. If an amine is on a chain, it has to be the lowest number possible. If an amine and an alcohol are in the same compound, the alcohol gets priority and the amine gets treated just like everybody else. An amine can be seen as like a chlorine or a fluorine. So if we were looking at this really simple change to propane, alcohol group, well, that's the only branch. Even if it was a Br or a CH3, well, CH3 would expand the chain, but if it was a methoxy, this would be the first carbon regardless. So it would be propan 1-ol. And remember, if it's a singular alcohol or singular amine, propanol or propanamine, we drop that E. But if the moment we have more than one alcohol or more than one amine, whereas a diol or a diamine, we retain that E. Let's look at this. Straight across, we have a pentane. It's a 5-carbon chain. However, both ways across, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Which way do we want to go, black or blue?
Black.
Black, because it gives the lowest number to oxygen no matter what. So you want to give the lowest number to oxygen, even if it gives the other branches really high numbers. So you could have a like 7, 8, 9 trimethyl decanol. If it gives alcohol that first carbon, you have to go with that one, even without the regard of the other branches. So this would be 3, 4 dimethyl pentanol. It's always a good habit to put that one. I think it's multiple choice for you guys, so I think you guys could get away with seeing that one or not. But if you're writing it out, we would accept both. You don't have to write the 1-ol if it's on that first carbon. Now let's get into amines. We have a what kind of chain? 1, 2, 3, 4, a butane, and then we have an amine group on that first carbon. So this is when it's really easy. Butan. Remember, drop that E if there's only one butanamine. 1, 2, 3, 4. Now, this is the tough one we're looking at. This is our longest carbon chain. It is a hexane for 6 carbons, but our only branch is an amine and a CH3 on that amine. Now, that CH3, whatever branches are on the amine, we treat as normal branches. If this was an ethyl group, we keep it as an ethyl. As you see, this is a methyl group, so it's a methyl hexane amine. What number would go here?
2.
2. Lowest number possible. But for the methyl group, even though it's a branch, we have to know what it's connected to. And we just put N. It just tells us it's on that amine group. That's it. Anyone have any questions?
For the going back to the alcohol one, did you mean to put 3, 4 dimethyl pentane 1-ol? Or did you mean to put 2-ol? That's what I meant.
Yes.
See, I thought it was a
My bad.
2-ol.
My bad. My
Okay.
bad. All right. Now the branches are really stupid. But kind of easy to put together. So you guys know like your propyl, your ethyl. I don't think we went over branches in class, in all honesty. But let's just go with this example just so you guys know. Well, when you're converting these branches of branches, like if you have a decane, all right, and then you have a branch chain on that decane, that's something it's useful for. You just put an AL between that Y, an AN between that P and the Y. Propanil and ethanol. All right. And between these, you just denote a number like 2. Excuse me. And that number correlates with what part of the branch is attached to. This would be a butan 2-ill. And you don't have to combine it with the main chain. We're just asking about what that branch would be called. I know it's a little confusing, and I'm kind of sad he didn't go over in class, but in person, he doesn't really go over in class that much either. But for this one, let's just take a look at the right. The longest parent chain, just treat as normal, is a propane. So it would be a propanil. And since it's connected to that first propane carbon, it's propan 1-ill. And that propanil has 2 methyl groups attached to it. So it would be 2, 2, that should be dashed, dimethyl propan 1-ill. Does anyone have any questions? It's kind of weird to wrap your head around. So I'm just going to throw another example out. All right, let's do, here. There we go. Someone want to take a crack at naming that? I threw a priority group on it, so it'd be pretty hard. If not, we'll just take a crack at it. Well, the longest carbon chain is a butane. So it'd be butanil. And it's connected to that third carbon. How do we know it's the third carbon and not the second carbon? Well, remember, we need to denote the priority group on the smallest or the lowest carbon possible. This is a really hard example. He won't throw something like this at you. It's going to be a alkane. He won't throw any functional groups at you. But this would be it would be a hydroxy. That's a bad example. This is a semester 2 correlated nomenclature. I'm getting a little bit ahead of myself. But let's just say, let's change it up. Let's make it to BR. There we go. Now it's a 2. Butanil. And it would be butan 2-ill. And with that bromine there, 3 bromo, butan 2-ill. Because you have our parent chain, butanil, is attached with its second carbon, and the butanil also has a 3 bromo attachment or branch. Anyone have any questions?
Can you go over which direction you named the second branched molecule?
Molecule? Yeah, this could go 1, 2, 3 or 1, 2, 3. I mean, it's the same both ways because our branch groups are on the same carbon. You just want to denote the smallest numbers possible, because if you went this way, it would be 2, 2 dimethyl propan 3-ill. But we want the 1-ill. So we want to go this way. Does that make sense? Or was this the one you're talking about?
Yeah, no, that makes sense. Thank you.
Okay, great. Now, hopefully you guys also watched that organic chemistry teacher video on this, because it's pretty helpful. Do you guys feel comfortable about bicyclic naming? I'm pretty sure it will come up on the test.
Wait, which video were you talking about?
I think it's the middle one I posted. I posted like 3 videos yesterday, and it's the
Okay.
middle one.
In the group me?
Yeah, in the group me.
Thank you.
The basic rules are you have 2 cycles and you have 2 bridgehead carbons. you count how many carbons are between them. So I'm just going to keep them black. I'm not actually numbering them. These are just counting numbers. We have 1, 2, 3, 4. 1, 2, 3. And we have 0 carbons between those bridge hydrocarbons. So it would be, it's a little thick, 4, 3, 0, denoting how many carbons are between the bridgehead carbons. All right. Now, in terms of numbering them, we have to start at a bridgehead carbon. 1, 2, 3, 4, 5, 6, 7, 8, 9. And on top of starting at a bridgehead carbon, we have to count around the first or the largest ring first. So if we go the other direction, 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to erase these real quick. There we go. So thankfully, we have a methyl group that's always on 8 both times around. So neither direction really matters. It's going to be an 8-methyl bicyclo nonane. Let's do it over here. Let's count the carbons. 1, 2, 3, 4, 5, 6. We have a 6. 1, 2, 3. 3 carbons and then 0 carbons between. Alrighty. Now, counting from the bridgehead carbons, let's go around. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. The other way around would be 1. Nope, wrong one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Which numbering system would be correct?
The navy one.
Yes, the navy blue one, because even though the light blue one gives methoxy a 4, we need to give OH the smallest number possible. And that priority cannot override the need to count around the largest ring first. But we still need to go in the direction that gives OH the smallest number possible, and that's with the navy. So if we use the navy, we would have a 5-methoxy bicyclo, and we use the total carbons present, undecane, 9 all. All right,
So you prioritize the OH over the methoxy?
correct, because it's a functional group. The lowest number possible. And the only numbers possible are 9 and 11. Because we have to start a bridgehead carbon and we have to go around the largest ring first both ways. Now let's mix the functional groups. Are you guys okay if I move on?
Yeah.
All right. Longest carbon chain. 1, 2. All right. This is a heptane, 7 carbons. 1, 2, 3, 4, 5, 6, 7, 8. No, that's an octane. I counted wrong. My bad. All right, octane. 1, 2, 3, 4, 5, 6, 7, 8. Which direction will we go? Black or blue?
Black.
Black. That's because we have a functional group and that needs the lowest number possible. And that's 2. Even if it gives bromine and methyl a 5 and a 7 compared to 2 and a 4, OH must have the 2. So it would be 5 bromo, 7 methyl, octan, 2 all. All right, now let's identify the parent chain here. All right, we're looking at the ends of the carbons. There's no other carbon chain attached to it, so we can't really extend it. So we have just a pentane. Let's number them. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Which way do we go? Black or blue?
Black.
It would be blue because this is an amine group. An amine group is a priority group, so it needs to be numbered the lowest no matter what. So if we chose the blue, this would be 4, this would be 5. So we'd have a 4-chloro, 5-methoxy, methyl pentan 2 amine. What will we put here? Someone want to shout out or throw in the chat?
An N.
Yep, we just put it in there. Now we're getting to a little bit of an interesting one. All
Why
right,
do you just put it in there?
because we denote that methyl group is attached to an amine group, because it's not attached to
Oh.
a number in the carbon chain, just the amine group.
Okay, thank you.
And we order it according, again, to alphabetical order. We just treat N as if it was a number, but we're just denoting that it's on the amine. So for this one, it's a ring structure, but we also have a priority group, an amine group. So we have to start there. 1, 2, 3. So it's gonna be 3-methyl. Well, we have a 3-methyl group. We also have a methyl group as here as well. And we also have an ethyl group. So it would be, I'm just gonna draw some brainstorming to see how I get to the final answer. 3-methyl, or it has to be N-methyl, N-ethyl. 3-methyl, N-methyl, cyclohexane, 1-amine. However, again, we can combine these, so it's just going to be N-ethyl, N3-dimethyl, cyclohexane, 1-amine. Does anyone have any questions? Great. Now, let's throw one of these at you. 2 priority groups or functional groups. Which one has priority? You can throw it in the chat if you want.
OH.
Yeah, OH. So this would be 1, 2, 3. Really easy. And again, if they're both present, NH2 becomes branch status. So we just put it in the prefixes. So the only time you will see an amino prefix is if there's an alcohol present as well. So it would be 3-amino, cyclo, pentan, 1-all. Now let's move on to this particular one. Now we have 2 sites, 2 pairs of branches where we can have a first pointed difference. Like if we started here, we can go either direction, we'd go towards the chlorine. Or if we started here, going either direction, we would have to go in the direction of the methyl group because we want to follow the lines or connect the dots of the most branches possible. However, there's a functional group here, so that automatically, no matter what, becomes the first carbon. So this is the first carbon. Well, it already gives us a direction. We have to connect the dots. So this has to be the direction we go for chlorine, or with chlorine. It's 2, 3, 4, 5, 6. Does anyone have any questions with that logic there? We start at what?
Patrick, real quick, I do have a question. So for the extension to like straight carbon chains, if you have an alcohol, say towards one end and towards the other end, you just have like methyl or ethyl groups, you would override trying to get the lowest number for any substituents in order to get the lowest number
Correct.
for that functional group.
Correct. Yeah.
Okay.
Correct.
Thanks.
You want to give alcohol the lowest numbers possible, even if it gives any other substituent, being amine, who's now at branch status if it's present, or any other branches, the high numbers. We just want OH to be the low number, period. Okay. So you're right. So it would be 2-chloro, 5-ethyl, 4-methyl, cyclohexane, 1-all. Anyone have any questions on how we got there? Cool. All right, let's move on to this. Now, this includes stereochemistry. You don't have to name stereochemistry yet. You will have to soon, but just keep in mind, these are pretty dead giveaways. if you see a line or a dash, you have to include stereochemistry. Or for this one, we'll just keep it as cis or trans. Or by that denomination, you'll see why. But let's just identify it. Is this trans or cis?
Trans.
Trans. Trans. All right, it's trans, and we have two alcohols. Well, it doesn't really matter where we start because we have 1, 2, 3, 4, 1, 2, 3, 4. Either way, it's a 1,4 diol no matter what. So our parent chain is cyclohexane, and we can retain that E and do 1,4 diol. Make sure you retain that E when we have more than one alcohol. And this we're just gonna put trans. In real life, later on we'll do E cyclohexane because E is shorthand for trans for us. However, you don't need to worry about that right now. All right, let's move on to this one. We have again both an alcohol and an amine. All right, so if we start numbering 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Which way do we go? Black or blue?
Blue.
Blue. Even if your instincts want to tell you we want to go black, so it's 1, 2, 4, we have to go with the 2, 4, 5 because the OH will have a 2. That's how we want to number it. So it would be 5 amino, 4 bromo, pen, tan, 1 all, or pen 2 all. My bad.
So we prioritize.
This would not be a hexane.
Did I write pentane? Yeah, it's a pentane. We have 5 carbons. Here, let me redraw it out. 1, 2, 3, 4, 5.
Oh, okay, I see. Because there's a amine group where the carbon I was thinking would have been. Never mind.
Yeah. Now let's get into isomers.
I have a quick question.
Yeah, shoot.
Do you prioritize the alcohols or the amines and aminos?
Yeah, you prioritize alcohols over everything.
Okay.
Yeah. Even if there's an amine group there, the moment that alcohol is present, the amine group becomes the same status as that bromo or a chloro or a methyl, just becomes branch status. All right. Now, do you guys know your definitions between different compounds, constitutional isomers, and stereoisomers? Hopefully you guys do. So different compounds is just straight up different molecular formulas. So the biggest giveaway for that is the same number of carbons. If it has a different amount of carbons, then they're different compounds just entirely. A big giveaway for constitutional isomers are different ring structures, like this one right here. We have a cyclohexane and cyclopentane. They're obviously not the same compound, and they're not stereoisomers because there's just different rings in general. It's the connectivity that's different. So a good candidate is either going to be different or constitutional isomers. Well, if we look at the molecular formulas, we have 1, 2, 3, 4, 5, 6, 7 carbons. 1, 2, 3, 4, 5, 6, 7 carbons as well. Same. All right. And if we were to expand, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 14 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 plus 3, that's 14 hydrogens as well. Same molecular formula, different connectivity. That's constitutional isomer. Now looking at this, all right, well, let's take a look. We have a 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. These are heptanes. Let me highlight parent chain. These are both heptanes. There's a good chance that they're the same. Let's number the carbons. 1, 2, 3. 1, 2, 3. This terp butyl group is on the third carbon in both situations. So they're the same. You guys following? Let's move on to this one. Are these the same, different stereoisomers or constitutional isomers?
They're different compounds.
Yeah, they're different compounds. This one has an oxygen, this one does not. Now, one of the questions that he could throw at you for this is making you compare one of these cuculae structures and a chair conformation. So to give us some practice, let's just pretend that O isn't there. Let's just pretend it's not there. All right. Would these be the same or different? Well, if we know that, here, let me copy and paste and bring it down here. Give me 1 second so that you guys know what I'm talking about. Where are you? There you are. Copy. Bring it all the way down here. I'm going to paste it. There we go. All righty. They are on the same side of that ring structure. They're going to be alternating axial, equatorial, axial, equatorial. Right? So if I were to draw all the same plane atoms on this ring, if this was axial, this would be equatorial, axial, equatorial, axial, equatorial. And by process of elimination, this one must be axial. So what I'm looking for is an axial and an axial. However, even though this one is axial, this one is equatorial. They would be different compounds because this is equatorial. Not what we're looking for. Does that make sense? Kind of. We'll try to see what we can do with the model set. Now for this one, I think the biggest giveaway are your branch groups. Now, does someone want to take a crack at what kind of structure these are? These are constitutional isomers, different, same, or stereoisomers.
Constitutional.
Yeah, they're constitutional. The biggest giveaway is connectivity. And this back ring is connected to both the ethyl and the methyl group. However, in this side, the back ring is connected to the ethyl group, but the methyl group is attached to this front ring. So that's a pretty good indicator that they're different connectivity. Now let's look at this one on the right. Are they different, same, constitutional isomers, or stereoisomers?
Would it be stereo?
No, they would be different, because if we were to look at the longest parent chain, well, look at the parent chain, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. Even though we have a butyl group on both sides and a methyl branch, the parent chains are different. This has one extra carbon than it should have. So they're different molecular formulas. For this one, are these the same, different stereoisomers, or constitutional isomers? You guys are welcome to also throw stuff in the chat if you want. Stereoisomers. The reasoning being, all right, let's look at this one on the left. This is axial, this is equatorial. Axial. From what we talked about the chart, or not really chart, the diagram up here, what must be special about these three if they're alternating like that? They must be on the same plane. All right. If equatorial is correlated with the adjacent axials, they're on the same plane. However, for these, they're on different planes because the CH3 is trans to the other two groups. So they're stereoisomers. Because if they were the same, we would have the H here and the CH3 up here. All right. Now for these last two, let's just take a crack at these. We have cis and we have cis. Both of these methyl groups are on the same side. Are they stereoisomers, the same, different, or constitutional isomers?
Same.
Yeah, they're the same. A way you can imagine this is just pancake flipping them. Or if they were in chair conformations, just a chair flip. If you chair flip this, it would look like this. They are the same. Now, for this one's a little tough because you're looking at 3 different stereocenters. So again, let's visualize these. All right, for all the wedges. All right, if this was axial, this one would have to be equatorial, axial, equatorial, axial, equatorial. That means for all the wedges, equatorial, axial, equatorial, axial, equatorial, axial. They alternate. So the CH3 should be axial. So if let me highlight these instead of circling them. All right. So if these are on the same plane, this must be on the opposite plane. All right. However, here we have the ethyl group being on a different plane than the 2 methyl groups, which is not what we want. Let me use better colors for this. Let me just reuse them. There we go. That's not what we want, because this one should be up here and this should be down here. I did that wrong. I flipped them. My bad. This should be down here. They're stereoisomers.
Do you think that it's possible he'd give us something of this caliber on the test?
Small chance. Yeah. By plane, do you mean equatorial, axial, or up and down? Same plane, I mean they're on the same side. So same plane just means they're all wedged. So if I have cyclohexane, axial, equatorial, axial, that just means they're all wedged. Because that's what we mean by this crown kind of deal. Same plane would be these, because if these are all whoops, wrong one. If these are all wedged, right? If you're looking top down, these would be dashed. So these ones are on the same plane when you're looking at it in that specific way. Does that make sense? Or do you guys want to whip out the model kits for this? Because we're done with the packet. So I think we can whip them out. They don't have any last minute questions regarding the review packet, because I'm thinking right now for the rest of our time, we're gonna, try to understand what we were talking about for isomerism with the model kits, and then go over the answers for that practice test I posted from 2021. You guys can react with thumbs up on the Zoom if you guys are okay with that.
This wasn't on the review packet, but could you go over the different types of strains that we learned today?
Yeah. Yes, I can. Whoops, wrong one. There we go. The different types of strains. So we have 3 types: bond angle strain, torsional strain, and steric strain. Those are the only things you have to list, like BAS, TS, or SS when you're working on the test. Bond angle strain is only seen in cyclic compounds. So that's a pretty neat thing. So if it's not cyclic, if it's like an alkane or a carbon chain, you can only have torsional strain or steric strain because there's no bond angle strain. It's not cyclic. And on top of that, if there's bond angle strain and that's usually seen in cyclopropanes, cyclobutanes, and cyclopentanes, then there's always torsional strain. The thing is, the moment it becomes a cyclohexane, that or cyclohexane and above, that's what that plus is for. 120 degrees and above, there's no bond angle strain because it's big enough. Does bond angle strain make sense for you guys? You only write it if there's a cyclopentane or lower. Okay. Are you guys good? Let's move on to torsional strain. Torsional strain is seen whenever there's bond angle strain because there's a force eclipsed, but mainly just an eclipse pattern. So if you have a planar cyclohexane, that also has torsional strain because it's not in a chair conformation. The only way to relieve torsional strain is by having it in a chair conformation when we stagger them. So these first two are really easy. All right. So bond angle strain only in cyclic compounds 5 and below. And then torsional strain is only in planar compounds or cyclic compounds. Just mainly because it's indicated by the eclipse. I keep forgetting it was Newman projection. Does that make sense? Steric strain can apply to any of these 3 types of strain. The moment the compound has any one of these 3, it has steric strain. So even if it doesn't have gauche, or if it doesn't have 1,3 diaxial, if it has flagpole, it has steric strain. So the moment it has any of these. Now, 1,3 diaxial is a type of strain you see when there are conformations with axial positioned alkyl groups. The only way to relieve this is, again, if you have it in a less energy filled state in the equatorial conformation. But if it's an axial, this C or this CH3 in real life has hydrogen sticking out of it. And those hydrogens will fuck with each other because of electrostatic forces. Does that make sense?
I have a quick question.
Yeah.
When, like, on the practice test, if it asks for, like, it will ask use BAS, TS, or SS, will it ask us to name the specific type of steric strain or just?
You just
Okay.
have to write, yeah, just write
Okay, thank you.
SS. Gauche is, again, if you have it in staggered, we have 2 methyl groups attached to each other. Any kind of alkyl groups. So if you have a CH3 neck, or that's gauche with an H, that's not gauche. If you have a H gauche with another H, not gauche. But if you have alkyl groups like CH3 or a ethyl group or a propyl group, if they're next to each other in a staggered formation, it's going to be gauche. So there is steric strain. The only way to relieve that is if they are opposite of each other. So like if this CH3 was here, all right, that would not have steric strain because they're away from each other. Flagpole is if you have a boat conformation and you have methyl groups right here. So it's kind of the same thing as your 1,3 diaxial. If you have methyl groups or any kind of CH3 or ethyl group attached here, they will fuck with each other, and you don't really like that. The only way to relieve this is if you have this conformation flipped down, or if CH3 is in the equatorial position. This one is a little bit of a rare case, and you only see it if there's a boat conformation. So even though we see 5 examples, there's only 3 types of steric strains that you have to identify. But those are the 3 you see, or not 3, the 5 you see. Anyone have any questions regarding that? All right. I think it might be a good idea. Let's just go ahead and blow through the answer key for the practice test I posted. Did anyone do that? Hands, if anyone did it. Yeah. All right, let's go over it. Oh, Kevin, you're at lab. Oh, some of you guys were in lab. Well, let's go through it. We'll see if you guys ran into something. So I have more copies. So if you need more practice or answer keys, just come get me and I'll grade them. But let me find that answer key. Jeez. There we go. It's version 1. Too many files. The one I sent is version 1, right?
Yes.
All right. Let me send it over. All right, here's the key. All right, so the first one, again, we have. Ooh, no, I'm not gonna fuck with it. The longest chain is an octane. It goes around the corner twice. Tell me when you guys are ready to move on. Ooh, something to note here. For this pentane, the alcohol is in that middle one, 3-ol. So it's 1, 2, 3, and 1, 2, 3, both sides. So either way works. So that is a time where you have to use the alphabet as a tiebreaker. Gavin, for reasons I can't post answer keys, so you're always just welcome to send me what you have, and I'll just look at it and tell you what's wrong. I'm sorry, man. This one right here, this is the example I used in my video. This one, I think when I was going through it, I got it wrong because I forgot that I have to go this way, or from this O to that OH. Because if we start at this OH, you would get low numbers for the OH this way, or an unreasonably high number for the amino group. So in order to minimize the denomination for the diol and minimize the number for the amino, we have to go from this OH to this OH, because no matter what, the alcohols have to have the lowest numbers possible, period.
Just making sure for the last one, you keep the E on the pentane because the prefix of the ol is di. But if you only had one OH group, you could omit the E from the pentane.
Correct. Yeah.
Okay.
You guys go with me scrolling down, or you guys still grading this? It would not be 5 amino, it would be 4. Because if you started from this one, it would be 1, 2, 3, and 4. 4 amino. The reason why you wouldn't go around is if it's 1, 2, 3, 4, 5. Well, it still satisfies the 1, 3 diol, but compared to this direction, we get a 4 amino compared to a 5 amino this way. And you wouldn't want to go this way from this O just in general, because if we went this way from that O, it would be a 1, 4 diol, which is breaking the rules because we need the diol to be a 1, 3, the lowest possible numbers, because it's a priority group. I'm gonna scroll down to the next page already. Now this stuff gets a little interesting. So do you see here how Dr. Berg identified the acids in both? These conjugate bases, he didn't even bother writing the pKa. He just focused on writing the pKa for each of the acids because that's what it's correlated with. The pKa for ammonium is 9.2, but for HF is 3.2. Which one is the lowest pKa? It's 3.2, smallest one, so it's a stronger acid. It'll dissociate the most and push equilibrium away from the strong acid. So it's shifting to the left. For 3, if you're looking at which is the strongest base is the weakest acid. The weakest acid has, well, no inductive effect. So this leftmost one is incorrect because it's more acidic and thus less basic. Now you're comparing this and that, the middle one and the rightmost one. Now, strongest base, again, weakest acid. Which one is the weaker acid? It's going to be NH minus, because if we're looking at across the periodic table, which we are because N and O are in the same period, O is more electronegative than N. So if this was protic, it would be a lot more acidic than NH. If O is more acidic, then its conjugate base is less basic. So again, the strongest base is the least acidic. And for this situation right here, again, Lewis acid, you have a central atom and an incomplete octet. And it's usually with the correlation with 3 halogens or 3 hydrogens. AlCl3 is a really common Lewis acid. The aluminum has an incomplete octet. CCl4 has a complete octet. NaCl is just an ionic compound. C2H2 is just an alkyne, which is just a 4-atom chain. And NaNH2 is a Lewis base because it is an electron pair donor. That central nitrogen has an extra lone pair. 2 of them, in fact. So the Lewis acid is AlCl3. For this bicyclic compound, again, you have to number it starting from a bridgehead carbon. You have to count around the largest ring first before you count the smaller ring. So O has to be either 7 or 9. You have to go in the direction that goes, or that gives the OH a 7. Pentane 2-il, we have a pentane. We just add an AN for the pentyl and it's connected to the second carbon. The shape of SO2, we did that on the problem set, is bent. Same plane. Well, for this one, it does not give us a reference atom. So the easiest thing is just pick an sp2 carbon and just work from there. Because sp2 has to be planar with some shit. So sp2 is connected and in the same plane with all of these. This C is sp3, this C is sp3. It's a plane breaker. This N is sp2, so this C must also be the same plane. Everything connected to it must be the same plane. The most acidic proton, well, this is the only proton attached to an electronegative atom, so that one's pretty obvious. Boat conformation, torsional strain, because there's an eclipse formation between these 2 carbons, and you just have to write SS. You don't have to write 5-pole, but it is present. And that is present in the boat conformation. And for this one, there's torsional strain because they are eclipsed. Moving on, hybridization of C4, that is sp2, 3 bonds. C6 is also sp2 because there are 3 electron groups. For O2, that's tetrahedral because don't forget those lone pairs there. It's sp3. N1, there's a lone pair here, so it is sp2 and not sp. C4, C4 is an sp2, and just knowing from how bond angles derive from hybridization, sp2 is always 120. Same thing with O2. O2 is tetrahedral, so it'll always be 109.5. The degree of unsaturation, that's an equation you should know, it's 5. And C7 is connected to an oxygen and then 1 carbon, so it's primary. looking at, let's just work from the bottom up. These are the same because follow along these carbon chain. There are methyl groups on the third and the fourth chain on that heptane. For these ones, stereoisomers, we have equatorial, equatorial, equatorial. However, Br and CH3 are right next to each other. And if they're both equatorial and next to each other, they should be trans to each other. But here they're cis to each other. These ones are cis just in general because this has one less carbon than this. Or I mean, one more hydrogen. Not they have the same amount of carbons, but different hydrogens. And they're one's a ring structure, one's not. This one's also pretty easy. Ring structures, but this has 6 carbons each, same amount of hydrogens, constitutional isomers. Same thing here. These are constitutional isomers because the back ring is connected to 3 methyl groups and the front one is connected to 1. However, the front one is connected to 3, all 3, and the back one's connected to none. So that's a pretty big giveaway that they're not the same. The front ring has different numbers of methyl groups than the back ring in both situations. This one's just plain simple. It gives us a reference Newman projection, and we just draw it out. All right. And this middle conformation, yeah, we can go over the degree of saturation. This middle conformation has these methyl groups the farthest away from each other. This one has a 4 in a row, and this one has 4 in a row. So this one limits that gauche because this has 1, 2, 3 sites of gauche steric strain, and this only has 2 sites of gauche steric strain. Excuse me. For this one, all right. So knowing the axial and equatorial positions is super helpful for questions like these. So if we have CH3, CH2, CH3 here, and CH3 here, they are trans to each other and they're on different planes. So if they're 1, 2, 3 away from each other, this is axial. If we draw something here, this, let's just say top side is here, bottom side is here. Top side axial, top side equatorial, top side axial, bottom side equatorial, bottom side axial, bottom side equatorial. So axial, equatorial, like we did. And then if we do a chair flip, we just literally just flip these. So we rewrite it, but just swap them. CH3 being an axial, H being an equatorial, and then flip-flopping this alpha group into equatorial. And then we have to circle the most stable chair conformation that has the biggest group in the equatorial position facing away from the chair conformation. This is the most stable. And then we do the same thing here. We have top side, bottom side, bottom side. So top side, bottom side, bottom side. Top side axial, top side equatorial, top side axial, top side equatorial, or bottom side equatorial, bottom side axial, bottom side equatorial. We see that here. We have the top side axial, equatorial, axial, equatorial, axial, equatorial. And then for the chair flip, again, just flip-flop them from that position and then choose the most stable conformation. The one on the right has 2 out of the 3 methyl groups in equatorial positions. So that's the most stable one. Because this one only has 1 CH3 in the equatorial position. Are we good on that? Going back up, let's go to the degrees of saturation. So the formula for the degrees of unsaturation is C minus H/2 plus 1. So if there are 8 carbons, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. Wait. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, there's a nitrogen too. Let me see. I'm going to type the formula in chat. C minus H/2 plus, yeah, plus 1/2, because whatever however many nitrogens you have, you divide that by 2 like you do with H, but you add that. Eight minus 4.5 plus 0.5 plus 1 gives you 5. So 8 minus 4.5 is 3.5, plus 0.5 gives it 4, plus that final 1 makes it 5. Is everyone ready to move on to chair confirmations? Give a thumbs up in the reaction images or the chat if you're ready to move on. If not, I'm just gonna wait here and let you guys draw this stuff out. Okay. Cass is ready. All right, cool. Well, let me stop my screen share. Ready. Disconnect. It's been maybe like half a year since I whipped this puppy out. So with the black pieces, I just make little tetrahedral stuff like this. Okay. So hopefully you guys are making along with me. I'm just making a bunch of these. You know what's really funny? My ex gave these to me and I still have them. Now I'm a TA and I'm not giving them. I'm not passing it down. It is a good gift. Hella good gift. Who knew? All righty. Right. I have my hexagon ring structure. And what I'm doing is for every single top side, I'm going to do the white beads. And every single bottom side, I'm going to do black beads. Not black beads, red beads. Like this. I also remember my first semester when I was fucking with these, the first time I whipped the shit out was when I was high as fuck. And it was really fun. I highly recommend it. Oh shit, this is a recording. I'm self-incriminating myself. I'm gonna edit this out later.
Edit
All
it in
right.
post.
What's up?
You'll edit it in post.
Yeah, I'll edit it. I'll have to cut shit out. Whoops. All right. So this is what you should have. Top side all red. Bottom side all white. Okay. So you see how they already are kind of like bending in on each other. The only way to relieve that is in a chair conformation like this, right? So if you observe it here, every single white bead is cis to each other. So if this was a BR, this is a CLO or CL. If you do a chair conformation, well, would you look at that? This bead is axial, while this bead is equatorial. This bead is axial. This bead is equatorial. They alternate. And if you do a chair flip, it all reverses in on itself. So if you do a chair flip, keep an eye on this axial one, chair flip, it becomes equatorial. And this formerly equatorial white bead becomes axial now. Something you're welcome to do is keep this ring structure on the test, right? Let's say you have, you're looking at 4 different groups. Let's say, no, 3 different groups. 2 of them are cis, 1 is trans, right? So you don't have to do this on your thing, but just look at mine. So if I'm keeping 2 of the white beads, 1 of the red beads, because these 2 are cis, this one is trans. If I were to ring conformation, all right, well, in order to relieve torsional strain, you can see if you look down this is staggered. This one is axial. Oops, no, equatorial. This white bead on the same side, cis, is equatorial. This one is axial. However, 1, 2, 3, 4, or 1, 2, 3, this is axial. This one would hypothetically be equatorial, axial, equatorial. But this opposite goes for the red one. You have no idea what you're doing with the model. Here, let me whip these puppies back out. I'm just putting the white beads back on. All right. Create or visualize 3D. I'm sorry to hear that. I don't know how else to fix this. I'm also hindered by a camera. If you guys were able to see this in person, it would help a lot. But just knowing the fact these white beads, all right, if you just look at them, just know, okay, in a chair conformation, they would alternate axial, equatorial, axial, equatorial, axial, equatorial in a chair conformation. And we see that chair conformation, axial, equatorial, axial, equatorial, axial, equatorial. Same thing if it was on the other side, because the reverse is true. This away one is equatorial. This axial one is perpendicular. It's just axial, equatorial. The bottom side also alternates. Again, everything on the same plane. If you're looking at this like top down, let's say you're looking at this on a paper, right? All of these white beads would be wedged. They would all be wedged, and that's what you would see. So if these were all wedged and they're on the same side, let's just say we're looking at these 2. Focus on the red ones. All the white beads are dashed, and both of these red ones are wedged. If we do a chair conformation, well, if they're next to each other and they're wedged, they're on the same plane. However, notice one is equatorial, one is axial. Knowing the alternating behavior of same-sided beads is the fundamental rule. All right, it's the fundamental. So same-sided beads alternate in a chair conformation. That's all you have to know. You can interpret pretty much anything from that. Does anyone have any specific questions about this? Call this my crown.
I just want to make sure real quick. Let me turn on my camera as well. Do I have this set up right?
Let me see.
Wait. Oh, Zoom's not gonna let me use my camera now. Okay.
It's not.
Wait. Oh, there it goes. Okay.
All right.
So like this.
Yeah. So you see how all the
Okay.
white beads.
Yeah, I at least was able to get that far, and then I got confused when it comes to like bending it and how all that works.
The chair flip, you have to kind of do it simultaneously. Let me whip this shit out. Yeah. Mm. The chair flip, visualizing like this, hands on both flagpole tips.
So like here and
Yeah.
here-ish.
Yeah, right across from each other. So if you're cyclohexane,
Yeah,
your
okay.
hands are on 1-4 positions.
Yeah, okay.
You just flip them, you rotate it, and they'll naturally rotate.
So God, I'm getting so confused with this. This is like the one thing on the exam I'm not confident with. Everything else I feel like I'm fine.
That's the downside of having it online.
Yeah.
Sorry, guys.
I blame VT more than anything. They're the whole reason I'm even here for the summer.
Yeah. Yeah.
I'll probably just tomorrow mess around with this a bit more and see if I can figure it out.
And in all honesty, my suggestion is you don't even have to have all the beads in here. Let's do an example. Here. You guys can see this? Let's take a look at this one right here. You guys can see my screen, right?
Yeah.
Yes.
Okay.
Yep.
Cool. Well, we need one with a chair confirmation. That's not a good one. Right here. There we go. So we have this one right here. So the left side is a chair confirmation, but the right side, we can actually work our way around. So they're all on the adjacent 3 carbons. So let's strip 3 of these things off. So all we have left is basically half of our ring structure like this. Right? React with a thumbs up when you're done with that. We're trying to mimic this right side, by the way. I'm going to assume, okay, you guys are good. So you see how this BR, CH3, CH3, they're on alternating planes. So if I'm just going to say, let's just say the white is the top half, right? I'm going to remove this middle one like this. And then I'm going to remove these red ones on these 2 sides. So all I have left is an alternating yellow and white kind of crown. You guys see that? So this basically tells us, okay, the white ones represent the CH3 and the BR. They're on the same plane because they're both on the top half of that Hayworth structure. CH3 is on the opposite half of that Hayworth structure, so it's on the opposite plane. Now, let's look at this left image, all right? If we were to have a confirmation, let's make this confirmation. All right. If we were to change it so that, hold on. Okay. So the right side, the left side has our 2 top halves, CH3 and BR, axial. However, the CH3 that we denoted is also axial. However, it's denoted as equatorial here. So they are stereoisomers because the 1B difference of it being there instead of here makes them different structures. Same connectivity, just they're just stereoisomers of each other. You guys getting that?
More or less.
Yeah. I'm kind of sad that he spent only what, a day and a half on this. I don't think he has a class tomorrow, right?
We have class, but it moves on. So nothing for the exam.
Yeah. Yeah. I'll grade you guys' problem sets tomorrow. But my tip before we end this is just keep the structure, hold on to it for tomorrow. And however the beads are for that Hayward structure you're trying to compare, because it might come to you during the test, right? You just have blank template. All right. White beads, top half, red beads, bottom half. So CH3, alternate, because the middle one is bottom half CH3, and then BR up here. Let me find a green one. We'll use that green as BR. Why not? Like that. All right. And then if that's what our Hayworth is, let's see if that Hayworth structure is accurate with that chair conformation. Chair conformation, we have an axial, axial, and an axial. However, what I see is an axial, equatorial axial. So they must be different. Or different isomers. Let's take a look at this one. So let's just, again, pretend that O does not exist, and these are just CH3s, okay? So for the rightmost one, we are looking, instead of a Hayworth structure, we're looking at a cyclohexane that just tells us they're trans. Oops. So this CH3 is on one half. That's top side. However, in the fourth position away from it, this is dashed. Right? You see that? That's what that cyclohexane cuculated structure is trying to tell you. They're away from each other. Okay, they're trans from each other. Now, if we were to do a chair flip, Come on, work for me. All right, chair flip. Both are equatorial. And chair flip again. Both are axial. However, in the drawing I see on the left, one is equatorial while one is axial. And when they alternate, they would just be axial and equatorial. So I know that they would be stereoisomers. You're welcome to give Dr. Berg's videos another watch. That's something I would suggest. But those are the tips I have for trying to use your model set. Just keep these as cyclohexanes and have fun, play around, making them into chair conformations and see what you can do. Look, when you make chair conformations, whoops, I'm almost gonna break my thing. Look at chair conformations, try looking down the carbons. See if they are staggered or not. Look for that stuff. Right? Does anyone have any final questions before we end the call? And by the way, for any OChem class in the future, you're welcome to have your model set. The final, any upcoming tests, all of it, you can have your model set.
Thank you.
Yeah.
Thanks.
Yeah.
Thank you.
See you.